Okay, so let me do a quick intro before I let this monster go with anybody in the Millshaw. We're doing it up here for safety, Director of Information Technology, Director of Information to Health, Director of Finances. They're all some inversion chord on each other, first or second order, all of which are their own first orders that have second order and third order operations to what hydrogen is when you add relativity first to it. It's easier to start teaching kids daily operations. Here's a unit, human operate or human. ADP is operations and human resources. Excuse me. And that's kind of the first thing. Do you start with the people do you have? Or do you start with the skyscraper build we need? I know I need an aquifer over there. Some maintenance team on the cemetery program, leasing out the contracts, doing things. The relativistic Schrodinger's equation of the shortest distance, or how you add in. Let me just run through this real quick here. Might double this up as my interview. This stuff. And as much as I'd love to walk across water and do every bridge's DOT, and start from once you learn how to do one bridge program or what the route is for a salt crew winter program, they add in pretty specifically. But if you don't know that, then you have to derive it with a relativic equation, and that's going to be that port source at scale, or any real NP core that goes into that. When you say I got ultramarines and husbandry programs and everything else that have that same basic I thought I did another one here. There was supposed to be another math between these two about complex analytics or something like that, and he's breaking out EX and your general FX function, and how to understand these equations, or which teacher was doing it instead of teaching Fourier transfer or something in a class syllabus. I could do that because that is what this review is. There might have been another teacher that had done it before me that you're trying to replicate these individual building bricks and semi-imperial mass equation to that up and right heat decay thing with silver mine adjustment, so you don't mess up silver and wheat on rig guidance of the updated brief on what going for. I don't know, you'd want to start under the superintendent of the job required, recruit into this, and then if you had to hire other contracts outside of the place that do that, because they're bigger engineering features. And I got some videos here of a couple. This is the guy gets talking about the HUD gear that you're looking around, you shut things off, turn them on. Well, there's an analog base to it, and figuring out with Paragon here is a little different about how to recertify something in that way. With this isn't the one, but this is a good one. There's a 5-minute video to it, a 10-minute video to it, in this multi-metric trippy geometry that describes what you're doing. Let's get him ripping.
Hey, I want to tell you real quick why it is that the Schrodinger equation is not compatible with special relativity. The reason I want to tell you this is that in part 2 of the hydrogen video, we saw that the Schrodinger equation can give us a really good idea of what's going on inside of a hydrogen atom. But the Schrodinger equation is not actually 100% true. It's a non-relativistic approximation. And in hydrogen part 3, we're going to see what happens when we take the relativistic effects into account. But the really cool thing is that when you take relativity into account, it's not just that you get a slightly more precise number, but actually the ideas of relativity open up a whole new world of spin and antimatter and really trippy geometry. So today I want to take as the starting point the Schrodinger equation for the hydrogen atom that we derived in hydrogen part 1. And now the question I want to ask is, okay, well that's for hydrogen, but what about for a free electron that's not bound to a proton? In fact, imagine the proton's not even part of the story anymore, okay? It's just an electron. Well, to get that, all we have to do is delete the electrostatic potential term in the equation. So that E squared over 4 pi epsilon naught r times psi, just delete that, and the electron will be released from the grip of the proton.
Like it or not, humankind will end.
We should never have let AI out of the box.
You gotta do it up like an SK class apocalypse and the human civilization on the planet
You're my
going
friend?
nuts.
She dies with the rest of them.
I can't do that.
When you do that, you end up with the Schrodinger equation for a free particle, and notice now there's no charge term anymore, so it doesn't really matter that it's an electron. Could be any particle. Anyway, if you look at this equation, you see that there's a Laplacian and it's proportional to a time derivative, and so if you've worked with vector calculus before, you'll recognize this as a wave equation, where the more pinched or the more scrunched together the wave function is, the faster it's changing there, and the more flat the wave function is, the more kind of just uniform and not super pinched, well, the less it's changing over there. Now, right from the start, I want to tell you why this equation is relativistically problematic. If you look at the Laplacian, that's a second-order derivative. But now if you look at the time derivative, it's first order. And so in the same equation, we have a derivative that's second order in space and a derivative that's first order in time, and that doesn't really mesh well with the fundamental ideas in special relativity, in which space and time are unified into this 3 plus 1 dimensional Minkowski spacetime. And long story short, because of Lorentz boosts and the fact that different observers might take different slices through that spacetime depending on how fast they're going and where they are, you really don't want to have an equation where space and time are of a different order. Because the Lorentz transform is going to mix your space and your time together, and then it's just going to break the equation. So I know that's a bit of an abstract point, but I just want to say right from the start, you look at the Schrodinger equation and you say, oh yeah, that's not relativistic. Alright, but we want to get more specific insight here. So in order to be more specific, let me introduce the plane wave solutions to the Schrodinger equation. Today we're going to use the plane waves to explore how the Schrodinger equation behaves at a variety of different velocities, so that we can see that in the relativistic limit, the equation does not match experiment, and also has some theoretical issues as well. One thing I should say about these plane waves is that these are momentum and energy eigenstates. So these correspond to particles whose momentum is precisely known, but as a result, in quantum mechanics, you know the momentum, you don't know the position, so as a result, these plane waves go across all of space. Now, you can think of that in two ways. First of all, it's an idealization. In reality, you never perfectly know the momentum. But also, you can think about these plane waves like we're pretty zoomed in on the particle. So let's say you have some experiment and you're firing electrons with some momentum that's pretty well known, and then you're zoomed in on the region of interest in the experiment where the electron beam is pointing. Well, at that point you might as well model it as plane waves, even though if you were to zoom out and look at the laboratory and your experimental apparatus in context, it's not just a plane wave that goes on forever. So anyway, you don't have to take these plane waves too literally. But also, the other thing is you can stack these Fourier style. So let's say you don't precisely know the momentum, but maybe the momentum is some Gaussian thing. So for example, let's say you have a particle at rest, and you think it's at rest, but you're not exactly sure, maybe it has a little bit of momentum. So here on the top left in the plot, I'm showing a Gaussian distribution of momentum, so now momentum's kind of a fuzzy thing, we don't know exactly what it is. And then on the right, I'm showing the time evolution of that particle, where over time it's going to kind of spread out. The wave function is going to become more and more diffuse, but to actually calculate that, all you have to do is stack a bunch of momentum eigenstates and integrate over this momentum space. And here's a one-dimensional view of that, just to make it a bit more concrete, and I'm not going to get into the math in depth today, but long story short, if you're familiar with Fourier analysis, you can imagine that these momentum plane waves let us translate between momentum space and space. So anyway, all that's to say, by exploring the properties of these Schrodinger plane waves, we can get essential insight into the nature of the Schrodinger equation more generally, in a variety of contexts. Let's go back to that picture of the electron beam in our lab.
Kinda.
So what I'm showing here is a 10 keV electron. Now, if you haven't heard about it before, what is a keV? keV is a kiloelectron volt. So if you take an electron and you accelerate it down a voltage drop of 10,000...
So, while I get a couple of minutes left inside of here, this is the task. I know Schrodinger's equation seems like a simple FM 3-0 to talk about in today's safety brief. This would be early intro, dominate the baseball coach's lecture for public works, because, we have a free hand and I'm down a coach and we had a extra minute with one of them that can enrich them a certain way. So you're going to run and do that syllabus like that, quote the kids out, teach them how to do that, passively do that, try to keep it on the train. And as far as getting it from the Vatican and state funding over there, you got to show C++, not just fudge the numbers because, come testing later. Iron photochemistry here is going to tell me a few ways to determine, what the core material is, the temperature from these triangulations, with, whatever's going on here with some complex computation. So, hope that helps.